Hi, everyone. We're going to get started this evening, and I just want to thank you for attending this evening's event. First, on a couple of series that we'll be showing quarterly to our alumni and donors and guests and friends of Penn State and Earth and Mineral Sciences. I'm Alan Shafranek. I'm the Director of Alumni Relations, and I have the wonderful pleasure of welcoming and introducing Dr. John Morrow. So we want to thank you, John, for attending. And John is the Dorothy Pate Enright Professor of Material Sciences and Engineering, who continues to show the best the college has to offer through his research in areas of glass science, thermodynamics, statistical mechanics, and a variety of other disciplines, in which he is considered a world-renowned expert. We're proud to have him as a member of our faculty and as our speaker tonight. So, John, if you would like to take it over and share your screen, please.
Great. Thank you so much, Alan, for your kind introduction. I'm going to share my screen here, and I think I need to swap views. Great, let's get started. Thank you everyone for coming today. The title of my presentation is Lion Glass: Setting New Standards in Sustainability. My name is John Morrow. I'm a professor here in Material Science and Engineering. And what I would like to do in this presentation is to give you a little bit of background on the importance of glass as a material and how it helped to bring human civilization to where it is today. We'll take a little peek in our, not crystal ball, but our glassy ball to take a forward-looking look at some of the new applications of glass on the horizon. I'll tell you a little bit about my own personal journey in glass, a journey that led me to Penn State and my wonderful group of students here. And then I will finish up with some of our exciting new research on line glass. So glass is a material that we often look through rather than look at. And as a result, many people don't really pay attention to glass as a material itself. It's often something that we take for granted. And I was delighted to see this article that was published in The Atlantic, where glass was listed as humankind's most important material. Glass has changed the world like no other substance, but people usually overlook it. And earlier this year, the cover story of the February 2024 issue of National Geographic was devoted to the glass age. The history of humanity is often described in terms of the materials that have had the greatest impact, whether it's the Stone Age, the Bronze Age, the Iron Age. And there's a pretty good case to be made that we are now living in the glass age. So glass is one of the key enablers for modern civilization and scientific discovery. Things we take for granted, like the glass windows that are in our homes and in our office buildings, to keep out the harsh environment and to provide a good thermal barrier and mechanical barrier between the inside and the outside. Glasses for lenses for corrective vision. Glass lenses have also been critical for the development of the modern field of astronomy using telescopes instead of just the naked eye, as well as glass lenses to enable the field of microscopy and discovering, for example, the existence of microorganisms and germs that are responsible for diseases. All of this is enabled through glass as one of the key tools for scientific discovery. There's also glass packaging that is used for food and beverages, and in this case, pharmaceutical packaging. Right now, we are holding this seminar by transmitting information at the speed of light through optical signals over very thin strands of high purity silica glass. This is known as fiber optics. These each have the thickness of a human hair and can carry immense bandwidths of information at the speed of light. This was the key invention that brought us into the information age and enabled the invention of the internet. And it's not enough to just transmit that information. We also have to be able to display it. Advanced glass technologies have been critical for all televisions, computer monitors, screens of all types, whether you go back to the old cathode ray tubes or modern flat panel displays. All of that has been enabled by highly engineered pieces of glass. There's also the computers that we carry around in our pockets, smartphones, where now the primary way for which we interact with our computing device is through a glass touchscreen. So rather than through a keyboard or through a mouse, people are touching the glass itself, and that glass has to have the appropriate um, touch properties to enable the transmission of the electrical signal, as well as high mechanical strength to survive drops. And of course, glass has been key in transportation of all types, whether it's automotive, trains, planes, and so on. Glass is what keeps us safe while enabling us to be able to look out of the vehicle. Looking forward, glass has, of course, brought us to where we are today with respect to information technology, but there are a lot of new opportunities for advancements. For example, Samsung and other companies are working on ultra-thin, flexible, or even foldable displays that are based on thin glass substrates. High refractive index glass lenses are required components for augmented reality glasses where you can superimpose images, virtual images, on top of your real reality. Ultra low loss optical fiber is also going to be key for quantum communication. This is where we transmit quantumly entangled photons to enable perfectly secure communication. And glass is also a medium for high density memory storage, where glass can be stored in 3 dimensions rather than 2 dimensions. And that memory storage can have a much longer life compared to traditional magnetic memory storage. Looking forward in transportation, windshields and automobiles really haven't changed that much over the past several decades. There's a great opportunity to use advanced glasses to enable stronger, thinner windshields that will ensure the safety of the drivers and vehicle occupants while also lightweighting the vehicles for improved fuel economy. And as we move towards more autonomous vehicles, there are going to be more screens on the inside of cars. And those screens, of course, will need to be made from scratch-resistant glasses. From an architecture point of view, one of the next advances is going to be in vacuum insulated glazing. This is where instead of having a noble gas between the two panes of glass, a vacuum is pulled in order to minimize the amount of heat conduction across the window. And this creates a mechanical stress that the glass must be able to survive. And so the fatigue resistance of the glass is really key there. Glass is also being used to help enable the Internet of Things and bringing touchscreens and internet connectivity to devices and to rooms that haven't had it before. Acoustic damping glasses are also important, especially for people living in the city. Glass is also key for renewable energy generation. High elasticity, high stiffness fiberglass is key for windmill turbines. And to improve the efficiency of these windmills, we need to go to larger turbines, which means stiffer fiberglass. Companies like Owens Corning are working on developing the next generation of fiberglass compositions to help support wind energy. And when it comes to solar energy, glass plays multiple roles. Glass can be a container for photobioreactors that convert solar energy to chemical energy through photosynthesis. They can provide the substrates for the conversion of light directly into electricity through photovoltaics. They can convert light energy into thermal energy and then into electricity via solar thermal energy generation, which involves parabolic mirrors together with a glass tube that contains a polymer that can be heated with the focused light energy. And in addition to energy generation, glass may be a medium for energy storage. John Goodenough, who recently passed away, he was a Nobel Prize winner, co-inventor of the lithium-ion batteries, and up till the day he died, he was still working on new glass compositions as next-generation batteries that would have higher energy storage density, greater cyclability, and greater safety compared to today's batteries. Glass will also continue to play an important role in healthcare when it comes to medicines, vaccines, and so on. We need to be able to store those medicines in a container that's not going to react with them. So it needs to provide high corrosion resistance and high mechanical strength. Um, Also, glass can be made to be antimicrobial through a silver ion exchange at its surface. And so, for touch screens that are used in places like hospitals or places that might have multiple people using their touch screens, like at ATMs, antimicrobial glass surfaces can help prevent the spread of diseases. And finally, glasses can actually be embedded in the body to help stimulate the body's natural growth and repair processes. Glasses can be used for to stimulate bone repair, tooth repair for hard tissues, as well as soft tissue repair. For example, for diabetic patients that have ulcers, glass fibers can be designed to pack into those ulcers and provide the pathways and the chemicals that the body needs to help heal itself. Now, as materials scientists and engineers, we typically think about materials in terms of their properties and the engineering applications that we can use them for. But it's also really important to note the more cultural aspects of our materials, including glass, and the impact that they have had. For example, as artistic media. This is an example of the beautiful stained glass windows from Sainte-Chapelle in Paris that are about 900 years old. And glass was chosen as the medium for these stained glass windows because of its ability to take on different shapes, different colors, because of its optical transparency, because of its high corrosion resistance and high strength. And because of all these properties, this glass is still here with us almost a millennium later, and people can go there and view the beauty of this glass. So all of these properties that we value from an engineering point of view are also critical for use of the materials from an artistic point of view. So I think that that's important to keep in mind. And for all of these reasons, for all of the huge impact that glass has made on human society up to this point, as well as all the possibilities for glass in the future, the United Nations actually declared the year 2022 to be the International Year of Glass. This is the first time that the UN General Assembly has ever devoted an entire year, an international year, to a material. So I'm very grateful that they selected glass as the material of choice. Now, my own journey in glass started when I was a young child. I was 6 years old, and my parents took me to the Corning Museum of Glass. And I immediately fell in love with glass as a material and all the different shapes and the colors that it can take on, all the beautiful artwork that could be made. I was really captivated by it. And I didn't realize that it was a valid career choice until I saw this great video from my friendly hometown university, Alfred University, talking about their glass science program. And it all clicked for me. I knew that this is what I wanted to do. So I went to Alfred University. I did a double degree in glass science and computer science. And from there, I went to Corning Incorporated. I worked at Corning for 18 years. Corning is one of the world's leading glass and ceramics companies. It's based in upstate New York, the only Fortune 500 company that's left that is based in upstate New York. And I spent many years there working on all types of glass products. I started off working in optical fiber. I spent several years working in optical fiber design, optical systems, and networks. From there, I worked on glasses for displays, so for flat panel displays, trying to develop both the fundamental glass chemistry and physics for the design and understanding of new glasses, as well as applying that knowledge toward practical industrial needs and new glass design. Most famously, I of course worked on Corning Gorilla Glass, and this was a lot of fun to be able to go from, predicting what an optimal chemical formula would be to actually making it in the lab and scaling it up and doing the plant trials and then finally releasing it as a product at the Consumer Electronics Show in Las Vegas. So it's quite a ride to be able to go from the basic science to a new product that is, has been adopted by billions of people worldwide. And it has been truly a joy. Now, my first interaction with Penn State actually came as a result of philanthropy. I was the winner of the Voldemort A. Weil International Glass Science Award, which is given out by Penn State every 3 years to a young glass scientist worldwide. This is named in honor of Professor Voldemort Weil, who was one of the early pioneers of glass science at Penn State. Professor Weil was the one who developed the science of colored glass. He's got a wonderful textbook on colored glass that is still in use today. And Professor Carlo Pantano, who was the glass science professor here at Penn State before me, he was able to present me with this award in Brazil. And he invited me out for breakfast that morning and sort of asked me, "Have you ever thought about being a professor?" And encouraged me to think about it. So he put the bug in my ear, and when I went back to Corning, we noticed that it was becoming increasingly difficult to find well-qualified people to hire in the field of glass science because a lot of the professors that my colleagues and I had learned from were retiring and not necessarily being replaced by other glass science faculty. So we were seriously concerned about our ability to be able to hire people and for the United States to maintain its competitive edge. We did a study that showed that the US was really stagnating in the field of glass science, while at the same time China was growing exponentially and now more than doubles the research output in glass science compared to the US. So this was a serious problem for Corning. We tried to do what we could to help encourage universities to invest more in glass science, hire more glass faculty. And we were really concerned when we learned that Professor Pantano here at Penn State was going to retire. And my former boss at Corning told me I took a little bit too seriously when I quit my job there and came here to Penn State to be a faculty member in materials science and engineering. And I've got no regrets whatsoever. What we found here was really the perfect community for both this type of research and for having just this wonderful, healthy, energetic, respectful, vibrant community. And so my family and I all feel really passionate about the community here. And we were able to very quickly build the country's largest academic glass research group. I'm really fortunate to be able to work with so many great students. This is a partial group photo. We have about 20 people in my group right now. This is a bunch of my group that actually went to my hometown of Alfred, New York for a conference there. And it was a lot of fun to be able to bring everyone back there and show them around my hometown. Now, one of the projects that my group is devoting a lot of attention to is Lion Glass. And the problem that we're trying to address here is the carbon footprint of the glass industry. So, as much as I'm very proud of all the great work at Corning and how successful, say, Gorilla Glass has been, the fact is that that's a very small amount of glass compared to the standard soda lime silicate glass, which is used for every architectural window, automotive windows, every glass, just about every glass that you drink out of, all the glass packaging for jars of food, bottles, beverage packaging. That's all soda lime silicate, and it has not changed in a very long time. And that is responsible for over 86 million tons of carbon dioxide released into the atmosphere every year. About 70 to 80% of that carbon footprint is due to the energy required for the high temperatures for glass melting. The remaining 20 to 30% of it comes from decomposition of carbonate batch materials. Soda lime silicate is called that because two of the main ingredients are soda ash and limestone. Those are sodium carbonate and calcium carbonate. And when they melt, they convert to oxides. They're releasing carbon dioxide in the process. So Lion Glass is our solution to this problem. It is named after our Penn State mascot, the Nittany Lion, because let's face it, all the best glasses are named after animals, right? And Lime glass is designed to reduce the melting and forming temperatures by about 400 degrees Celsius compared to standard soda lime silicate. So this is a really dramatic reduction in the energy requirements. Lime glass also eliminates the use of carbonate batch materials. So we eliminate the carbon footprint due to the batch to melt conversion process and reduce the carbon footprint from energy consumption by a significant amount as well. So the tables here in the middle show the gases that get released from melting 125-gram batches of either soda lime silicate on the top or lime glass on the bottom. You can see that for a 125-gram batch of soda lime silicate that reduces or that emits 24.1 grams of carbon dioxide, so really significant amount of CO2. For lime glass, that reduces to 0.3 milligrams, so it's orders of magnitude reduction in carbon dioxide. So this reduces energy costs and carbon footprint. One of the other wonderful properties of lime glass is its improved mechanical damage resistance compared to soda lime silicate. The upper right plot shows the probability of soda lime silicate cracking under a Vickers diamond indenter with increasing load. Its crack initiation threshold, which is where the probability of cracking is 50%, occurs at about 0.1 kilograms force for soda lime silicate. For lime glass in the bottom right, at that same force, there's a 0% probability of cracking. And in fact, if you multiply that by 10, going from 0.1 all the way to 1 kilograms force, there's still just a 25% probability of cracking. So the crack resistance has been improved by more than a factor of 10 in lime glass compared to soda lime silicate. And the improved mechanical performance of lime glass can be a pathway to help enable the lightweighting of glass products because the improved mechanical performance can be traded off to go to thinner walled, lighter weight products, which of course has additional environmental benefits from reduced batch material consumption, reduced energy, reduced transportation cost and energy requirements. And one final feature of lime glass is that it does have improved ultraviolet absorption in the near UV compared to soda lime silicate. And so if this is used as a packaging for any products that are sensitive to UV degradation, such as cosmetics products, beverages, and food, there's some additional protection there provided by lime glass. Now, we partnered with a company in the Netherlands called Celsian to do some studies of the batch to melt conversion process of soda lime silicate versus lime glass. They have a furnace with a transparent crucible and a transparent window with a camera, so they can actually take a video of the batch to melt conversion process. And that video is what is being shown on the right here. And these are the batch materials for soda lime silicate. The current temperature as it's being heated up is shown in the upper left corner of the movie. So you can see that this is approaching 1100 degrees Celsius. And as that is happening, you can see that the carbonate batch materials are decomposing to oxides. They're releasing carbon dioxide in the process. The left-hand plot here shows the concentrations of gases that are being released. This is the CO2 concentration divided by 100 just to fit it on the same scale. And if you integrate that curve, you get a total of 24.1 grams of CO2 for every 125-gram batch. Now, when you get up to higher temperatures, we're getting to 1350 degrees C. The fining agent kicks in, that's sodium sulfate, that releases SO2 blisters and O2 blisters. Those gases rise to the top, and as you get to 1400 degrees C and 1450 degrees C, there's a lot of foaming as the gases are being released up to the top. And then as we approach 1500 degrees C, you can see that things calm down. And then at this point, you get a nice homogeneous glass melt. But it really does require those high temperatures in order to get that high quality melt with soda lime silicate. So this shows the same thing with lime glass. This is the same size batch, 125-gram batch. And we're starting here. You can see the temperatures are approaching 700 degrees C. And even at this low temperature, you can see some of the batch reactions taking place. Now, instead of CO2, you see this is the actual CO2 concentration, not divided by 100. CO2 is reduced dramatically. So now for the same size batch, there's only 0.3 milligrams of CO2 released. Instead, the primary gas that gets released is water vapor. So the green curve is the water vapor concentration divided by 1,000. It's releasing something like 8 grams of water vapor for this 125-gram batch. The release of water vapor, of course, is environmentally neutral as opposed to being something environmentally harmful. And that helps with some of these batch reaction kinetics and mixing behaviors. So you see the water vapor is being released here, the gases are evolving. Again, sodium sulfate is used as a fining agent that releases a peak of SO2 blisters to help with the fining and homogenization. And as we get 900 degrees C, this actually looks very similar to what we saw in soda lime at 1400 degrees C. The bubbles are rising to the top. We're getting a nice homogeneous glass at about 950 degrees C. And approaching 1,000 degrees C with wine glass. So in this case, the melting temperature was actually reduced by about 500 degrees C compared to soda lime silicate. So that is a dramatic reduction of the energy requirements in addition to eliminating carbonate batch materials. This is my student, Aaron. He is, in addition to being a scientist, he's also a glass blower, and he was demonstrating the first ever blowing of wine glass. I think my movie's a little bit choppy here, but a lot of the properties that are required for a glass to be blowable are the same types of properties that are needed to be able to make glass bottles. And so he is actually using our glass studio and in a beautiful demonstration of STEAM, this science, technology, engineering, art, and mathematics education, using our newly designed glass composition with a lot of science built into it, using that as an artistic medium to demonstrate the engineering properties as well as the artistic properties of this glass. And so here's another piece of art that was made by my postdoc, Nick. He made a nice flower here out of wine glass. And moving forward, so the latest news is that we've got an official partnership with an Italian glassmaker, Bormiolo Luigi. Bormioli Luigi is based in Parma, Italy, and they are one of the leading suppliers of glass packaging for cosmetics. And here they are visiting with us in our lab. This shows some of the products that they are making. You can see some of their customers include Prada, Chanel, Christian Dior, and so on. So they supply a lot of the major cosmetics companies. And so this is the target to be the first product using wine glass. And in fact, Chanel has told us that they would like the next generation of Chanel #5 to be packaged in wine glass. There's a big demand for going to greener packaging in this industry. And this is also, of course, much smaller volume compared to containers for beverages or architectural windows. So we're starting here, while at the same time working on a number of collaborations with other companies as well. But more news on that later when I'm able to talk about it. For now, I would like to thank you for your time. Thank you for coming, and I'm happy to take any questions.
Thank you, everyone. John, we do have a couple of questions that came in. One of them is, what are the primary goals with the collaboration between Penn State and other vendors? Is this something where Penn State would be making revenue from the partnerships?
Great question. So we would be licensing the technologies to glass companies and also working with them to help with the engineering scale up. So the idea is that we license our patent to them. They would manufacture line glass using our technical input and partnership to help them deal with whatever scale-up issues that come up. And then Penn State would receive a royalty from that. And then we would be able to use that royalty to help offer scholarships to students, to help support research, and basically help create this virtuous cycle to give more people the opportunity to receive a Penn State education.
Wonderful. Thank you. We have another question that came in, and it is there a collaboration effort with respect to windshields?
With respect to windshields, so great question. We don't have anything official yet. We are in negotiations on flat glass for both architectural and automotive applications, which would include windshields. I've met with automotive companies as well as with the glass companies making the glass for those applications. There is a lot of interest, and we're going to make it happen. It's in the pipeline.
That's very exciting. It's great to hear that. Another question that came through is, what are the future directions of Lion Glass, meaning research and development? And how do you feel that Penn State is on a path that they're going to continue innovating in other areas such as glass?
Oh, yes, yes. So this is just one of many areas of glass research that we do in my group. I've got several people working on Lion Glass. We've already had two generations of intellectual property on that, and I anticipate several more generations to come as well. One of the things that we want to do is to use the royalties from this to help support materials research as well, so we can always be at the forefront of the science and technology here. My group also does research in all types of fundamental and applied glass science for other applications, including biological applications, optical glasses. We work in glass ceramics. We've got projects for dental glass ceramics, for example. So there's a lot of interesting research going on. And that's just my group. The Department of Materials Science and Engineering has over 30 faculty members with expertise across the full range of materials, metals, ceramics, glasses, polymers, composites, 2D materials. And so Penn State is one of the world's leading institutions in materials science and engineering. We're part of an amazing college, the College of Earth and Mineral Sciences, where every one of the five departments is one of the world's leaders in their respective areas. And so it's really a powerhouse here in the College of EMS.
That makes us all very proud to be either Penn State alums, staff, or friends of Earth and Mineral Sciences. One last question that has come through is, it's a collaboration and a commercialization question. And what challenges have been encountered in transitioning Lion Glass from the laboratory and innovation into the market-ready product that is happening with Birimoly?
Sure, sure. So glass manufacturing is a very capital intensive process that it's very difficult to make large changes because you can't just stop a glass melting tank. You'd have to undergo continuous transitions, and the sheer volume of glass that is produced in industrial glass tanks is just so much bigger than anything that we do in small scale crucible melting in an academic setting. And so any changes that are made in industry, it takes a lot of time and a lot of money. And so you need to be absolutely sure that you're doing exactly the right thing to make it work properly. So there's a lot of checklists that are specific to each company to make sure that we understand all the properties of the glass and all the process moves that need to be made to make sure that we can go in and do it right and not mess things up with their glass manufacturing.
Wonderful. Thank you for that answer. And we have another one that came up as well. Are there advantages using this process for memory applications, specifically looking at speed and or access to data?
Okay, so for memory, so I would encourage you to Google Project Silica. So Microsoft has a project called Project Silica, where they are using glass as a memory storage medium. Um, I I don't think that Lion Glass would offer an advantage for that. I think you'd want to have kind of higher temperature glasses that have basically more heat resistance to them compared to Lion Glass. But um, that's an interesting thought. But glass in general, just speaking generally from glass, has advantages compared to other memory storage media because When you store the memory in glass, that can last for millions or billions of years, as opposed to magnetic memory storage, which really can only last a decade or two.
Great. We have another question that came in.
Mhm.
Are there sufficient raw materials available at reasonable cost today to scale up to float glass tank volume?
Great. So yes, we're working with a partner to address these questions. So I can't give the details of that, but yes, all of the batch materials that we use for line glass, although they're different from soda lime silicate, they are commonly used and available in the agricultural industry. So they are available.
Great. Well, that is all of the questions that have come through. If anyone else does have a question, feel free to put it into the chat, but I think we may be all up to date on our questions. So unless there are any more that come through, I'm going to begin to wrap everything up. And I want to thank you, Dr. Morrow, for coming on and talking to us about Lion Glass, this new spectacular thing that's happening within Earth and Mineral Sciences and the Department of Material Sciences. So I know there's going to be so many more updates coming in the future. So would love to feature you again, but thank you so much for coming on tonight.
Thank you too.
Absolutely. And I would be remiss if I did not thank our other guest, Tony Ferret, who is on with us. This program would not have been able to happen without her as well. So she's one of my colleagues here in the Office of Development and Alumni Relations for the College of Earth and Mineral Sciences. And I do see we have another question that came up. This question is, are you utilizing any type of AI to monitor the manufacturing process?
No, I'm not doing that. We're very a small scale here with our crucible melting. Individual companies may have their own systems for that, but that's kind of outside of the scope of what we're doing with line glass.
Okay, and any other last minute questions before we wrap up? Okay, we will be providing a recording of today's session, and we'll also have some more information of how to contact myself, John, and Tony. So you're welcome to send any questions our way once you get the link to view the program. And I have to thank all of our guests who came on, our viewers. We would not be putting out this content had it not been for you jumping in. So I want to thank everyone again. One last thank you to John for coming on, and Tony, thank you so much for your help to put this on. I hope everyone has a great evening.
Thank you.